Hi, in this video we will solve problem number of islands asked by many companies like Amazon, Microsoft, Adobe, Apple, and Bloomberg. Hey, so now let's check out the first problem on graph data structure. Yes, we are starting graph data structures from this series, right? And this is the first problem. So before jumping to the problem, I want you to go through the few basic topics of graphs. Okay, although I will cover few of the things, few of the concepts here as well in video, but it will be more specific to problems itself. Okay, so try to cover few basics prerequisites for the graphs and then you are good to solve problems. So now let's check out this first problem, number of islands. So given an m cross n 2D binary grid, right? 2D binary grid which represents the map of ones. So ones is treated as a land, right? So this is as treated as land. Zeros is treated as water. Okay. And we need to return the number of islands, right? So we'll talk about this one, how we can connect to number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. So basically, what is an island? If you know that island is surrounded by water, right? So here one is land. So if I connect this one, this will become my island because this is connected, surrounded by water, right? Everywhere is water, and this is will be called as one island, right? And you can traverse, basically you can see the adjacent lands. That's a very good point, that horizontally and vertically. That means from one, you can either move horizontally or vertically. You can't move in diagonally. Okay. So this can be your part of land. This, if we have one, this can be your part of this. We have one. This can be your part of land. Similarly, this can be your part of land. So similarly, here you can see this is the part of land horizontally, then vertically, horizontally, this is vertically, so this is also part of land, and this is not a part of land. So I will consider this is my island. So if this is my island here, right, this will be my island, and one island will be this one. Okay, again here and here, in both these scenarios we have answer is two islands, right? So here, where I can write the answer, let me put it here, that answer is 2 here, as well as answer is 2 here. Okay. So these are islands, horizontal and vertically. You may assume all the four edges. So these were our four edges of the grid are surrounded by water. Okay. So you can might ask this question, right? How this can be a problem of graph? This is a simple problem by our 2D on 2D arrays. Yes, it is, right? So that's a problem, right? You can consider this as to be a problem of 2D arrays, but see how basically I'm saying that this is a graph. So basically, what is first graph is? So basically, graph is nothing, right? If we have one node, right, and we have an edge, this is called as graph, right? So this is called as node, and this is called as edge. So if you have node and edges, this will be called as graph. Okay, it can be as many number of edges, right, and nodes, right? These all are considered to be graph. So from graph, there is a sub part of it, right? Part of it that is known as binary trees. If you can know, right? We also solved problems on binary trees, right? So basically, where we have nodes and edges, right? But we have, when we have only specific two no two edges, right? Each node two or less, then it is called as binary tree. Okay. In graph, so this is graphs, this is binary trees. Okay. In graphs, we can as many as number of nodes, connected nodes, closed nodes, right? Like this one, this is also one graph, right? This here we have three nodes, right? And few of them is connected, right? This is also is a graph, right? So these all are graph. These are considered to be graph. So if you can see here, right, we have one, right? So consider that one as your one node, right? And this is connected horizontally, right? Second node. Then this is connected horizontally, one node. So if I represent the same diagram here of lengths, it is connected by this one, this is connected by this one, this is connected by this one, this is connected by this node, right? So basically this type of one island, right? This is one island. Similarly, we have this type of an island here. Here we have same this type of an island, this type of an island. So basically, if I'm saying I need to count number of islands, basically I need to count number of graph components. Okay, this problem you can see, I need to count number of graph components. Okay, so this is one graph, this is one graph component, this is one graph component. So we have two graph components here. Okay, similarly here, this one is graph component, right? This one is graph component. So two graph components here as well. Okay, so that's why this problem, you can consider this to be a graph. And how we will solve it? We will solve it by using graph algorithms, right? We will try to solve breadth first search, depth first search. So we will look into it. What is this breadth first search and depth first search is? Okay, so let's see first what is breadth first search. So let me create a figure. So here we have BFS. Basically, we have two graphs, right? And we will see what is BFS and DFS. Okay. So let me quickly name it. So suppose this is 1, 2, 3, 4, or let's name it anyhow 6, 7. This is 8. This is 9. Okay. Do the same here. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. So what is breadth first search? Breadth, basically this is two terms, right? One is breadth and one is depth. So if I am moving to depth, that is known as depth here, right? And if I am checking to the boundaries first, that is known as breadth. Okay. So what is breadth first search? In breadth first search, you will first go to the breadth, right? You will try out on that level, right? On that level, you will try all the all the nodes level by level. So suppose this is level 0, this is level 1, this is level 2, and this is level 3, right? So you will first reach the node levels by level. So you will first write 1, right? So 1. Then on the next level we have 2, 3, and 4. Then on the second level we have 6, 5, 7, and 9. And in the last level we have 8. So we will basically, my output of breadth for search will be like this one. We will do levels by levels, right? So basically, if I consider this first level, then I will reach second level, then this is third level and fourth level. If you can remember that in binary trees, right, we solve this problem by level order traversal. Basically, that is the exact same BFS, level order traversal. That is what BFS is. That was in binary trees, but when I am doing for graphs, that is known as BFS. That's it. Okay, now what is DFS? That is depth for search, right? It is first take consideration of depth. Okay, so that means you are at here. This is suppose your root node. Okay, so first you will print this one, right? Okay, first you will print this one, and then first you will cover the depth. So you will come to here, right? Then you will print 2. Let me use the red pen only. You will first print 1, then you will print 2, and then you will reach to the 6, right? Now, see, this is done. This is visited, right? You have visited it. Okay. Then 2 you visited. Then 6 you visited. And now there is no further routes. There is no further nodes and edges, right? So this, what you will do, you will come back. You will come back out of it. Again, you will come back out of it, and you will explore the next depth, right? So you will explore 3 then. Okay. Then you will explore the next depth. Then means you will explore 5. And once 3 visited, so you will mark this visited. When 5 visited, you will mark as visit. Again, you will come back, right? Again, you will explore the next depth, and that is not from 1, that is 7, right? So you will explore this one and you will visit 7. And once you will visit 7, you are not going to visit again. That's why you will mark it visited. Again, you will back it, come back from it, and you will explore the next depth, that is 4. Okay, you will mark that visited. Then you will explore 9. Then you will mark as visited. Then you will explore 8, and that you will mark as visited. Now here you have visited all the nodes, and basically this will be your output. Okay, so this is my output, right? Depth for search, that means I'm first considering depth. Okay, and this is how basically BFS and DFS is. Okay, DFS is more towards like your backtracking problems, right? In backtracking, if you can remember, right, when we have function calls, right? One function, I am doing one function call, right? Then we have suppose 3 function calls. Now from 3 functions call, I am doing again 3 function calls. Okay, so I am first exploring right? One of the path, right? I am exploring one of the path, and then I am reaching back to it. Then I am reaching back to it, right? Similarly, we will do in the DFS, right? We will explore the one path completely, then I will explore the second path. And you can try any path, right? You can try from left, then after you can do the right one, or you can do the right one first, then left one. Remember, whenever, whichever you started first, you will need to be stick on that only. So first you are visiting left, so you will visit left nodes all, then you are visiting right, then you will visit right nodes. Okay, that is all about BFS and DFS. I will give you a few things because now we are learning graphs, so you might come up with question, right? Where we store graphs, right? We have queue as a data structure to store, we have stack as a data structure to store, where we store graphs. Okay, so graphs will be stored in two ways, right? That is, one is adjacency matrix. Okay, what is adjacency matrix? You can check. Basically, we will create a matrix, right? And suppose we have two nodes, one is connected to two. So what I will do, I will simply mark row 1 with column 2, and then column 2 with row 1. Okay, that is in adjacency matrix. And then the second way is, that is more, because here in adjacency matrix we have wastage of memory. Okay, then the second way is adjacency list, so that you can also check it out. Adjacency list, that's a smarter way to store it. Okay, so it's a better way to store graphs. Okay, so that's enough prerequisites for graph. Okay, now we can simply go ahead and start solving this problem. Okay, so let me quickly draw one figure so that we can analyze it and we can start on it. So let's check out this example. Okay, this is my matrix, okay, of n cross m, matrix of n cross m, where n is representing rows, m is representing columns. Let me quickly create rows 0, 1, 2, 3, 4 and 0, 1, 2, 3, 4, right? So it's a 4 cross 4 matrix. Okay, 5 cross 5, sorry, matrix. We have 5 rows and 5 columns. So n is equals to 5 and m is equals to 5. Now here you can see what are your part of length. So basically these are your part of lengths, and I have not created water. Basically the remaining cells you can consider this to be a water. So this is one island, this is one island, and these two are separate because we can't consider this to be the same island, because we have given that you can move either horizontally and vertically, not in diagonally, right? So what I will do, I will remove this one, and this is also one part of the land. Okay, so this is, there are total 3 parts of the line, so the output is 3. Okay, now how we will solve this? Okay, so if you can think, right, that's a quite easy problem. If you can think, what I will do, I will check, I will first check, first thing, right, if do I have any part of a line. So I will first check where is the part of a line. So I will check the part of a land, right? Here I get part of the land. Now what I will do, I will I will move in 4 directions, right? I will move in 4 directions. What are the 4 directions? I will move in the top, then bottom, then on the right, then on the left side. Okay, so suppose if I have one pointers I comma j, and I have 4 possible directions. So if I am moving at the top, I will do I minus 1 comma j. If I am moving at the bottom, it will be I plus 1 comma j, right? If I'm moving here, it will be I same I with j plus 1. If I'm moving here, it will be I with j minus 1. Okay, so these are the 4 directions that I will move, right? So the next step will be move in 4 direction, all 4 directions. So I will move in the 4 directions. Okay, now once I am moving it, right? So see, from here, if I take green pen, right, if I am moving here, can I move it? No, right? Because boundary cases, I am getting out of the grid, out of the matrix. Again, I can't move it here because out of the grid. I can't move it here because water, right? But I can move it here. So let's talk about the edge cases, right? So what I will do, if there is a water, if there is a water, what I will do, I will simply return it. So when I need to return, when I have met of I comma j is equals to 0, right? What I will do, I will simply return that's a water. And when I'm crossing the boundary, okay, when I'm crossing the boundary of it, so when I am crossing the boundary, I will return from it, right? So what are the boundary conditions, right? Again, I if it is less than 0, or j is less than 0, or I is greater than equals to n, or j is greater than equals to n, I am simply getting out of the boundary and I will simply return from it. Now, see, so from here, right, this is not your path, this is not your path, you will not your path. Here you can move it. You will again move the 4 directions. Again, you can't move it here, you can't move it here, right? But you can move it here. So will you move it again back to the same cell? No, you shouldn't, right? You shouldn't move to the same cell. So what I will do, once I will move it here, once I will move it here, I will make this as 0. That means this is visited. Okay, I can take a track of it that I have visited, or I can make it 0. I can make it water. Okay, so again, that is your choice. Okay, once you move, okay, before moving, change the cell, or mark visited. Okay, I can mark it visited, that this cell I have already visited. So this cell I have already visited, I will mark it visited. Okay, so what I will do, I can visit this one now, right? So now once this is done, I can't move it here, move it here. Now I can't move it in the back. So what I will do, I will move it here. Again, I have 4 possible directions, right? So again, I can't move it here out of the boundary. I can't move it here, water. I can't move it to the back because again, water, right? Visit the cell is already visited, so I will move it here. Again, from here, I have 4 possible ways, right? Okay, I can't move it here, water. I can't move it here, water. I can't move it here because that is already visited. That is already visited. So I have made 0. So what I will do, I will visit it here. Okay, now again 4 possible directions, right? I can't move it here, I can't move it here, I can't move it here, I can't move top because that is already visited. So that's end, right? And I will make this also visited. Okay, now I don't have any path to go on, right? I don't have any path. What I will do, I will come back to the last function call, then I will come back to the last function call, and so on, right? I will come to here. So from this point, I have reached the all possible ways, right? So what I will do, I will explore this. So 0 comma 0, I have visited, I have checked from 0 comma 0 all the possible ways. Okay, now what I will do, I will check from 0 comma 1, that is water, so I won't go ahead, right? Because I have made it 0 water. Then what I will do, I will move to 0 comma 2, that is also water, so I won't go ahead, right? Similarly, I will check all these cells, right? So this is one of the way that you can do to solve this problem, that is DFS. Okay, we are basically first going to the depth of it, right? But like suppose you reached here, right? Suppose during function calls you will reach here, you can't move it here, you can't move it here, you can't go to the out of the boundary. Again, you will move it here, you will visit this one, this one, this one, and that's done, right? So after visited, okay, the fifth step is the last step. Okay, after visited, after coming out of it, you will update the count. You will say count plus plus after visited all cell. Okay, after explore all the cell. You'll say after explore the ways. Okay. So count will be count plus plus, and that is one of the method that we can solve. Okay. Then you can solve this problem one more method, that is breadth first search. Okay. What you can do, again, the same number, basically what you will do, if I take the same diagram of it. So basically we have traversal ways, right? So the two traversal ways we have, that is DFS and BFS, right? So we can solve by any of the traversal, either DFS or BFS. Okay. In BFS, what will the things? The things will be exact same. Again, you have 4 directions to visit, right? 1, 2, 3, 4. But what you will do? What you will do? You will basically you will take first point, right? Suppose you are starting from here, and you will store these. Basically you will find out the connected nodes, right? Because breadth first search, you will find out the connected node. This is the connected node, and you will store its row and column, right? So if I say row and column, so you will store its 0th row and first column, and that you will store in a queue. Okay, in a queue data structure, what I will do, I will store its row and column, and then what I will do, from my queue, until my queue is not getting empty, I will visit this one. Again, I will try to explore by whom these are connected. So 0 comma 1, right, is connected to this one as well as is connected to this one. So again, what I will do, I will make this to 0 or something as visited, right? Or if I'm not changing this one, what I will do, I can create an extra 2D array, visited 2D array. Okay, and in that case, what I will do, I can mention that suppose if this is 0 comma 0, right? So I can make 0 comma 0, like suppose this visited 2D array. Okay, I am creating a visited 2D array that has 0 comma 0. So I can make this as true. That means I have visited this one, so I won't consider. Even suppose if I have added it here, right, 0 comma 0 already visited. So what I will do, I will simply remove from my stack. Okay, I will simply remove from the stack. Then I will check this node how many items it is connected to, right? I will simply put in my queue data structure. Okay, and in that ways I can simply check it. Okay, I'm not going to the depth of it because in our JavaScript, right, queue data structure is not present, right? We can create, if we want to really want to solve this problem by using queues, we can use some head pointer, okay, and tail pointer, so that we can create a bit data structure like queue and we can simply traverse it. Otherwise, we can apply in Java, we have queue data structure, or we can create a complete new function or class of queue, and then we can solve this problem. But again, right, that's a good thing. You can explore this option BFS. You can learn about it, how to traverse, and you can search about how you can solve the same problem by using BFS. Okay, so that will be your work, that how you can figure out this BFS. That is, you can solve it by DFS. Now let's quickly try what will the pseudo code of it. Okay, so basically what we are doing here, I am exploring all the positions of my matrix. So I will start from 0. Okay, I will go till n, basically my matrix length. Then I will start from j, that is equals to 0, and I will go till m, basically my columns. And I will check if there is not water. That means if there is a land, then I will check it. So I will simply say if my mat of I comma j is equals to 1, that's a string. Then what I will do, then I will do a function call, right? And then my function call is suppose find islands, right, where I will pass the mat and I will pass my a, I and j pointer, that is 0 comma 0. And after, once I'm coming from it, I will simply do a count plus plus. So I will count it that this is one of the island. Okay, then what will be my find islands function is, basically if I create that function, quickly find islands. Okay, so that will be my mat comma I comma j. Okay, so again I will first write the boundary conditions here. Okay, so I'm not writing here basically all the boundary conditions. Okay, after the boundary conditions, because I have visited, so I will make met I comma j equals to 0. That means I have visited this one. Okay, and after boundary conditions, right, I will make one condition here. If suppose before this one, right, if suppose there is a water, because that is also possible that there is a water, right? So water condition, what is the water condition? That might of I comma j, if it is equals to 0, what I will do, I will simply return from it, right? So that will be one condition. I will simply put if here. Okay, and boundary conditions. Now once I have done it, then what I will do, I will, before moving to the next function calls, what will be my next function calls? Again same, find islands. Okay, my function calls will be, I can go ahead with I plus 1 comma j, right? Then same function call with met I minus 1 comma j, then same function call with met I comma j plus 1, then same function call with met, that is I comma j minus 1. So these will be the 4 direction function calls, right? And then what I will do, I will simply say I will return from it. Okay, but before moving to this, what I will do, I will make one mark that before moving, met of I comma j will be 0. So if you can see, we have done all these steps. First of all, check part of the land. So I am checking which is the part of the land here. Okay, and when the part of the land, then I am counting for the find islands. Okay, next is move in all 4 directions. So I am moving in all 4 directions. These are my all 4 directions, 1 2 3 4. Next step was water. If there is a water, return. If there is crossing the boundary, then return. So I am basically on boundary conditions, I am doing a return. If there is a water, I am doing a return. Okay, then next is before move, change the cell, mark it, visit it. Okay, so before moving, here I am changing the cell, I am changing it to 0. That means I have visited. I don't need to visit it again. Okay, so that I am doing it here. Then after exploring ways, I am doing count plus plus. So once I have explored all the ways here, then I am doing simply count plus plus. Okay, so these are the 4 steps. That's how you can solve this problem. Now let's quickly talk about the time and space complexity. So here I am doing recursion calls. Okay, so if I say, if I am taking consideration, right, from one function call, I can move to the next function call, then next function call, then next function call, and so on. So what will the time complexity? The only thing is I can reach to the complete grid if there are all ones, right? So the time complexity here will be big of n cross m, right? Basically, how many number of grids are present and how many number of basically grid cells are present. Basically, the total count will be our time complexity of my recursion function calls. You can say that we are also doing recursion calls here, like, so we are doing 4 recursion calls, so it will be big of n cross m. Yes, it will be, but again, right, the overall, right, if there is a 4 function calls, if I ignore it, right, basically it will be big of n cross m. That will be in extreme cases that in each cell I am calling these 4 function calls, right? There can be here once, so I will call it here. There can be here once, so I will call it here. So we are also not calling 4 function calls in entirely, right? So the time complexity will be big of n cross m. Now what about the space complexity here? So space complexity will be, you are not taking any extra space, but you are doing a function calls, right? And in the worst cases, suppose you have taken, if all are ones, right, you are calling this one, then calling this one, then so the recursion stack can go up to big O of n cross m, right? Again, that is a very, very worst case that can be possible, big O of n cross m. On the average case, it won't be. So it can be big O of n cross m, and we are not taking an extra space, but if you can consider the space of the given grid that was given to us, if you are taking that as in space, right? So then it will be big O of n cross m plus, right? So this was recursion stack, and this is for the grid that we are using. Again, that will be the time complexity will be because n cross m, right? So even time complexity will be big of n cross m, and space complexity will also be same as big of n cross m. So that will be the time and space complexity. Okay, and pseudo code is also clear. In the next video, I will give you a quick code implementation, right? Basically, what will be the code implementation of in JavaScript, and then we will do a bit of dry run for this code. Okay, so see you in the next video. We'll see the code implementation part.